yesterday's lecture, I don't know where it is exactly, but presumably you should have a link for the lecture notes from yesterday. So these are just the handwritten notes, essentially what I did yesterday. And so this should make it easier for you. I'm going to do the same for all the lectures. So, you know, if you don't want to take notes during the lecture, then you don't necessarily need to do that. And since I have some spies in the audience, they told me that it would help if I wait a little bit before switching slides so that you can finish copying whatever was on the current slide. So I'll try very hard to do that, although I'll probably forget. So we'll see. So by now, you know everything about massless spinors and massless amplitudes. And just to remind you, the place where we sort of left off yesterday was that we said that, so first of all, we said that the amplitude is a function of some couplings and momenta and polarizations. And at least for massless particles, what we said yesterday is that we can write both the momenta and polarizations in terms of massless spinors. So that gives us a sort of unified description of all the amplitudes. And now the thing that we want to do is we want to move to non-zero masses. So now we're going to talk about massive particles. And now we have some momentum where p squared equals m squared. And in this case, the question is, what do we do? Can we still express these guys in terms of spinors? So here the answer is very simple, because we already know what to do with massless vectors. We know that any massless vector can be written in terms of two-component spinors. So now we can take the massive momentum and split it into two massless momenta. So in this case, I'm writing P as K plus Q, where K squared equals Q squared equals 0. Now, once we've done that, then things are simple, because we can now express K in terms of massless spinors, the squares and the angles, and similarly for Q. Okay, and by the way, my iPad was well behaved. This morning, I tested it a number of times, and as soon as I start speaking, it suddenly is making those vertical lines. But hopefully it's gonna stay in, hopefully it's gonna stay under control. Okay, so let's think a little bit about what this involves. So I have a massless momentum. I have a massive momentum P, and I now want to write it in terms of these two massless vectors. And so essentially, the only choice we're making is we need to choose the direction of one of them. For example, this guy, K. So once I've chosen the direction of K, because K is light-like, that determines the full 4 vector. And the other thing that we know is we know that K plus Q squared is equal to m squared. And so that's equal to 2K dot Q. So everything is really fixed. I mean, once we chose the direction of K, everything is completely fixed in the story. So this choice amounts to a choice of some direction, some 3 vector. Now we can introduce a little more notation, which at this point is going to be a little obscure, but we'll get physical significance of that very soon. So instead of writing this in terms of some K and Q, we're going to write this P. We're just going to give these guys an index. So we have two light-like vectors. We're going to label them with an index that runs over 1 and 2. So I'm going to write them as Pi equals 1 plus Pi equals 2. So I have a new index taking two values. And so there's a new SU2 that's involved here. So this SU2 essentially rotates this P equals the I equals 1 guy into the I equals 2 guy. Now, as we said, once we've done this, we can write the vector in terms of massless spinors. So we can write now P alpha alpha dot is this P I equals 1 spinor, P I equals 1, plus the same thing with I equals 2. And now we're in the same position, or almost the same position, where we've written all our momenta in terms of massless spinors, only this time we need more spinors. So to write some complex massive momentum, we need 4 independent spinors instead of the 2 that we had yesterday. Okay, so this concludes the story for the momenta. Now let's talk about polarizations. So let me start by fermion polarizations first. So first of all, we're talking about spin 1/2 massive fermions. So in this case, we already saw that the Dirac spinor splits into two component spinors, and I need 2 different solutions for the 2 spin states. So this is kind of immediate. We simply write this UIP in terms of lambda I alpha and lambda tilde I alpha dot, or using the other notation that we just used with angles and brackets, angles and squares. So we can write the Dirac spinor like this. And this Dirac spinor satisfies the Dirac equation. So we have that P slash minus M times UIP equals 0. And that tells you that the 2 spinors go into each other once we multiply them by P slash. So P slash times PI equals M PI, and similarly P times PI goes to M PI square. Okay, and I'm usually not writing the slash. I'm just writing, instead of writing P slash, I'm writing P, because it's not contracted with gamma mu, but just with sigma mu. So, you know, it really means the same thing. Okay, so that's the story for the fermions. And what about vectors? So let's now talk about spin 1 massive vectors. So we already wrote down the polarizations in conventional form yesterday, and now we can just write them in terms of these new spinors that we introduced. So we have the plus polarization, which we can write as P1 sigma mu P1 divided by square root of 2m. So this guy, because there's an index I equals 1 here and I equals 1 here, we can refer to that as epsilon 1, 1. That's the plus polarization. Similarly, epsilon minus mu, the negative polarization, is the one corresponding to taking these 2 indices to be 2. So that's epsilon 2, 2. And epsilon mu 0 is 1 over 2m P1 sigma mu P2 plus the same thing with 1 and 2 exchanged. So it's symmetric under the exchange of the two indices 1 and 2 here. So this guy we're going to call epsilon 1, 2, which is the same. And the important thing here is that the 1 and 2 are symmetrized. So sometimes we're going to write this in a simpler form, or many times we're going to write this in a simpler form. We're going to write epsilon mu ij collectively as p underlined sigma mu p underlined over square root of 2m, where this guy is exactly what I wrote before. Epsilon ij alpha alpha dot is square root of 2 p underline divided by m. Now, let me explain a couple of things. So first of all, so I'm using this underline notation. What the underline means is it means that we're symmetrizing over the ij indices. So this means that I and j and the I and j indices are symmetrized over, just like we had in all of these cases. So this was 1, 1, this was 1, 2, and this was 1, 2, where we exchanged the one, where we looked at the symmetry combination. So in a way, if you think about this, it's not terribly surprising because we're constructing SU2 representations, and when you can construct those just from the basic ones, which are the spin 1/2 representation, and anytime you make an anti-symmetric combination, you get a singlet, and when you get and so the only non-trivial thing is to make a symmetric to take a symmetric combination. So this may sound a little mysterious because we haven't really talked about this, what this SU2 is really, but let's just, this is kind of, I'm being maybe ahead of myself a little bit, just keep this in mind. The second thing I want to mention is that I'm using this underline notation. This formalism is due to Arkani, Hamed, Huang, and Huang. This is in a paper from 2017, and in their notation, it's not underlined, but rather bolded. So whenever you have bolded spinors, it just means that you're symmetrizing over these ij indices, but it's very hard to bold when you just write something by hand. So I'm gonna use underline throughout these notes. But really this underline here is the bolded notation, or the bold notation that these guys introduced. Now, another thing that I want to say is if, so I wrote down all these relations here. If this sounds a little weird, just do it. Okay, this is an exercise. You should just, you can plug in the expressions for the two parts of the momentum. You can write the momentum as split it up like this and make sure that you get something that reduces to the thing that we wrote before. And one other comment to make, which I didn't emphasize maybe yesterday, is that remember in the massless case, we of course had some reference momentum that appeared for the polarization vectors. Now we don't, because these are, we're now talking about massive particles, so we don't have any gauge freedom. Okay, so are there any questions about any of this?
I don't see any hands up, so
Okay.
yes, we can keep going. Yeah.
Okay. Very good. Um, okay. So now we're in the same position. I mean, we have an amplitude that's where we can write everything in terms of massless spinors. So we have a uniform way of presenting all of our amplitudes. But let's talk a little bit about this SU2. So we said we're taking our momentum and we're splitting it like this. And there's an SU2 that rotates the two massless momenta. So let's talk a little bit about that. So we write our P as P. Oh, okay. This is good. This is not good. So this is Pi equals 1 plus Pi equals 2. Okay, I really tested this before and I thought it was the, I have this screen protector, but I don't know why it's doing that. I really have no idea. Anyway, so what is this SU2 doing? So this SU2 can rotate between this guy and this guy, but the thing that's preserved is the momentum P. And essentially, as we already said, the only thing we can choose here, we can choose the direction of this momentum, for example, and then everything is fixed. So this SU2 that we have here is related to possible choices of the direction of this moment of this light vector. And you see what it is. It's some rotation that we can make or some Lorentz transformation that we can make that preserves the momentum. So what this SU2 is, it's exactly the little group. Okay, I really don't know why it's doing this. So it's the little, okay, this is, I have no idea why it's doing that. So this is the little group. That's related to the momentum P. Okay, so let me remind you a little bit about the little group. So the little group is the subgroup of Lorentz transformations that keep the momentum invariant. And now we're talking about a massive particle. So the easiest frame in which to think about this is the rest frame. So in the rest frame, our momentum is just m0, 0, 0. And you see that the Lorentz transformations that leave this intact are the ones that rotate these three entries here, which is an SO3 or an SU2. So this is exactly what we're getting here. What the SU2 that sort of came in to the story is nothing but the massive little group. So, I'm really worried about this. Let me just pause for a second and see if I can maybe get a pen from someone because it seemed to be working just fine. I don't know if anyone had an experience like this before.
Okay.
With their
We'll take a couple of minutes, see if you can do that.
Yeah.
Sure.
Okay. Okay. So let me just give me a second.
Yeah. I use this exact same software. And I never had these things, but my guess is either it's the pen or the
Okay, I'm back. So someone told me that it happened to them before, and it's because it's heating too much. So it's not the pen; it's actually the iPad itself. So I just changed the position somehow. So hopefully it's gonna help it cool a little bit. But I hope it's just gonna get. I hope it's gonna get better. Um, okay, so let's see. Maybe it could take some time though for it to cool down. Okay, so what we're talking about is what we're seeing here is really the little group for the massive particle, which is in SU2. And then let's go back and talk about the m=0 case. So for the m=0 case, our momentum is of the form 1, 0, 0, 1. And in this case, the only Lorentz transformations we can make that keep the momentum invariant are things that rotate between these two guys. And so it's an SO2 or a U1. And if we go back and look at our massless spinners for the massless case, then it was then we really have a U1 hiding there. So remember that we wrote P alpha alpha dot is P times P. And you see that we can rephase this guy by some e to the I alpha and this guy by e to the minus I alpha. This is precisely the U1 the U1 little group that we're seeing here. Now, this alpha, if we're talking about real momenta, then this alpha is real. So for real momenta, this U1 is really just a phase rotation. But for complex momenta, it can be some complex number. Okay, so we're saying the U1 little group very, very explicitly when we rewrite our momenta in terms of massless spinners. And if you think about that, then under a little group, under the little group transformation, so suppose we make a little group transformation, then the various momenta, of course, stay unchanged. But the thing that does change is the spin direction. So the spin direction can change. So the things that really care about the little group are the polarizations. So if we have a scalar leg, the scalar leg is, of course, neutral under the little group transformation. If we're talking about a fermion leg, a spin 1/2 fermion, then this does care about little group transformations. If we're talking about a massive fermion, then this fermion leg carries an index I. So I can denote it with an index I for the spin 1/2 fermion. And then the massive SU2 little group that we talked about is acting on this index I. And if we're talking about a massless fermion, then if it has plus helicity, then it comes with a P, which under the little group transformation goes to some e to the I alpha P. And if it has negative helicity, then it carries the opposite type spinner, and that guy transforms with an e to the minus I alpha P. So in the case of massless fermions, because we're talking about a U1 symmetry, we can think of these guys as some U1 charges. So we're going to say that the plus helicity fermion has helicity weight, has a little group weight or little group charge +1, and this guy has little group weight -1. Okay, now we can move on to talk about massive vectors. So, so spin one particles. So for spin one particles, if we have something of a non-zero mass, then it carries two little group indices, I and J, because we wrote the polarization vectors before, and these carried two indices, I and J, which were symmetrized over. And if we're talking about a massless vector, then depending on its helicity, if it's on its polarization, if it has positive polarization, then it has little group weight +2. And if it has polarization, if it has negative polarization, it has little group weight -2. How do we see that? We just look at the expressions that we had for the massless polarizations. So remember that the plus guy was of the form RK divided by, by KR. And this K here is the momentum of the vector, and R was some arbitrary reference spinner. So you see that this is a square spinner, which we assigned charge or weight +1. And downstairs we have an angle spinner, which has weight -1. So altogether, we indeed get 2. And you can do the same thing for you can look at the same thing for the negative polarization. Now, there's also this arbitrary reference spinner that enters here, R. And you see that we have the same thing. We have an angle spinner R and an angle spinner R upstairs and downstairs. So there's no little group weight associated with that. Okay, so this is going to be very, very useful. In general, if we have some amplitude with some external leg of some spin S, let's say that it's massive, let's say that it's massless. If it's massless, it's going to carry a little group weight, which is equal to 2 times its helicity. So this is for the massless case, I want to label this leg by its helicity. So we basically know the little group weights of each one of the external legs. So these behave just like charges. So what this is going to give us essentially is all sorts of selection rules on the amplitudes. So we'll be able to say stuff about the structure of the amplitudes. Okay, so any questions about this before we go on?
Still no questions.
So at the end of the day, our amplitudes are going to be given by, once we put all these things together, we express our momenta, our polarizations in terms of the massless spinners. The amplitudes are going to be given by products or terms that involve different spinor products. So things of the form PI, PJ, let me for now, let me back up a little bit. So I can write everything in terms of massless spinors. And at the end of the day, things are going to be written in terms of some either square products or angle products of the form. Let me write this as PI, PJ anyway. So this is for the massless case. For the massive case, it's going to be a little more complicated because I should also have indices I and J here, but let's forget about them for now. So we're going to have things like this that show up or things like this that show up. And for brevity, we're usually going to label these just by other way around, IJ and IJ. And these are just the particle labels. I and J just label the external legs of the amplitude. There are some things that are useful that we should know about these spinor products. So first of all, for real momenta, these guys are related by complex conjugation. So IJ star is equal to JI. In general, if we look at 2pi dot pj, we can write that as pi alpha alpha dot pj alpha alpha dot alpha. And we can write that as the trace of pi pj pj, which is equal to ij times ji. All these things, by the way, are useful exercises. If it's like not immediately apparent, then that means that you should really do this. And so for real momenta, we see that these two products have the same absolute value. So this guy is equal to the square root of Sij times e to the I phi, and this guy is equal to the square root of Sij e to the minus I phi. And remember, my definition of Sij is just that it's the Lorentz invariant that you construct out of pi plus pj, and it's equal to 2pi dot pj for m equals 0 momenta. Okay. Okay, one last thing about these two-dimensional spinors that is very important and is totally trivial. It just follows from the fact that these two-dimensional spinors are two-dimensional. And so it means that we can span them in terms of a two-dimensional basis. So if I have any spinor K, I can always write it as some constant times I plus another constant sum J, where I and J are some arbitrary and independent two-component spinors. And these A and B are just some constants that are complex. And if we take the products of this equation once with I and once with J, you can convince yourself very easily that this B, for example, the constant B is equal to Ij divided by Ik, and similarly for A. Okay, and so when we plug this back in, when we plug this B in back into the equation, we get the following equation. We get that I times Jk plus J times Ki plus k times ij equals 0. And this is a very powerful relation between any three spinners. And if we multiply that by some other spinner, any other spinner L, we get a nice equation. We get that Li times jk plus the permutations of that is equal to 0. And similarly for the same thing with brackets, with square brackets. Okay, and these identities are called the Schlautern Identities, and they are very powerful in simplifying all sorts of spinner structures. Okay, so this was a lot of stuff and a lot of details and notations that we introduced. But now we can really put this to use, and it really simplifies computations. So that's why we had to suffer through all this. So let's do one example that I'm gonna kind of sketch, but you should really fill out all the details. If there's stuff, especially if there's stuff that you're not entirely sure about. So let's just look at a very well-known example, the example of Compton scattering. So we're going to calculate E gamma to E gamma using these techniques. And there are two reasons why I want to do this. First of all, just to demonstrate how things work. And the second reason is that we want to see exactly how these spinner variables simplify calculations. So I'm just doing a Feynman diagram calculation. My convention is always going to be that everything is incoming. All the particles are incoming. So I'm calculating an amplitude with E plus, E minus, and 2 gammas, or in general, some anti-fermion, fermion, gamma, gamma. And there are two diagrams that contribute here. There's this guy. And let me use 1, 2, 3, 4, which is not very sensible labeling, but that's what I did. And then the diagram with the photon legs exchanged. So what is this? So the first diagram gives us E squared, the coupling, times V1 bar epsilon 4 slash P1 plus P3 slash from the fermion propagator divided by P1 plus P3 squared epsilon 3 squared U2 plus the same thing with the exchange of 3 and 4. So this is completely standard stuff. Now, we see immediately that we have 3 gamma matrices. Here we have this guy, and this guy. So these two fermions have opposite helicities, or in other words, the helicity or chirality is preserved along the fermion line. And so there are two possibilities. Either this one is a P1, an angle spinner, and this guy is then a square spinner, or vice versa. So let me choose this. Let me make this choice. So this spinner we're just going to call 1, and this one we're going to call 2, like this. Okay, now I need to substitute the polarizations. So we call that the epsilon pluses alpha dot are of the form R K divided by KR. And epsilon minus is of the form KR divided by KR. And it's, when you look at this, it makes sense to take the same reference momentum for both of these guys. So I can choose this R to be, so sorry, I want to say something different. Let me first of all, right, so let me first of all make the choice that this reference momentum, the reference momentum is the same for 3 and 4. So R3 and R4 are both given by P1. And this is a good choice because it's going to simplify things. So we see that with this choice, when the epsilon 3 plus is next to 1, we're going to get 0. And similarly, if epsilon 4 is next to 1, we're also going to get 0. So we see immediately that if we have two plus helicity photons, we're going to get 0. So there's no contribution in this case, and we can conclude that the photons have opposite helicities. Okay, so now let's calculate some amplitude where the photons have opposite helicities. So we can take, for example, 3 plus and 4 minus. And then we can plug in the polarization vectors. So remember that in this case, let me write this again, epsilon 3 is of the form 1, 3 divided by 3, 1. And epsilon 4 minus is of the form 4, 1 divided by 4, 1. And so we just substitute that into this expression that we had here. And we get the following thing. There's a 1 over S13. There was the spinner 1 here. And then we have epsilon 4. So that's 4, 1 divided by 4, 1. Then we have P1 plus P3. So I write that as 1 plus 3. Then we have epsilon 3, which is 1, 3 divided by 3, 1. And then we just have the spinner 2. And then we have the other diagram with 3 and 4 exchanged. But then you see we have 1 here, and epsilon 3 is next to it, namely this guy, which has the spinner 1, and this thing vanishes. This thing vanishes because, remember, the spinner products are anti-symmetric. So if I have an II product, it just gives 0. So this guy goes away. This other diagram goes away. So now we can just look at this expression that we have left. You see that there is the momentum 1 here, but there's the spinner 1 appearing here. So the 1 does not contribute. It just gives 0. That's just the massless Dirac equation when it acts on the spinner 1. So I just have 3 that remains here. And so altogether, what we have is 1 over S13. We have this upstairs, we have 1, 4, 1, 3, 3, 1, 3, 2 divided by 4, 1, and 3, 1. So the 3, 1 cancels out. then I also have, I remember the fact that this S13 is equal to 1313. And so things just simplify and we're left with 1, 4, 2, 3, 1, 3, 1, 4. Now it's useful to just make sure that we got something sensible. So let's look at the little group weights of everything. So remember that R1 was a minus, R1 came with a angle spinner. So here I have one upstairs and one downstairs as angle spinners, but I also have one downstairs as a square spinner. So so that gives us a -1 altogether. So this one is okay. For 2, we don't have it downstairs, so we just have 2 here. So that little group weight is okay too. And for 3, we have it once upstairs with a square spinner and one upstairs with an angle spinners. So you can check that all the little group weights are okay. Okay, now we can simplify this a little more. Let me just show you this one thing, just so you know how to do these things. So upstairs, I have a 1, 3, and I have a 1, 4. So I can write this as 3, 1, 4, up to a sign. By the way, I'm not worried. I'm not keeping track here of signs at all. Just want to give you the general idea. So now we can use momentum conservation. This thing is equal to -3 times 2 plus 3 plus 4, because I just used momentum conservation to replace 1 by -2 plus 3 plus 4. So now the 3 acting on this 3 spinner is gonna drop out. So this guy cancels. Similarly, the 4 goes away. And so we can just write this as -3, 2 times 2, 4. And at the end of the day, after a few other manipulations like that, I can write the whole thing as some number times 2, 3 squared divided by 1, 4, 2, 4. So that's another exercise, is to fill in the gaps and just complete this calculation and make sure that you get to this final answer. So at the end of the day, we got something, we got something for this amplitude, but it's a very compact expression. Usually when you want to square the amplitude to get the cross-section, you need to work pretty hard and use all these U-bar relations and spin sums and so on and so forth. In this case, we just have a number. It's a complex number. In principle, we can substitute the expressions that we had for the spinners into this, and we just have something very simple in terms of the kinematics. So if you want to calculate things numerically, for example, it makes it very simple to do that. And it's also very simple to square that. If you want to calculate m squared for the cross-section, I just need to square this thing. And now we want to switch to real momenta. So this is just S23 squared divided by S14, S24. And because S14 and S23 are the same, we can get rid of this and this here. So you see that we get a very, very simple result. And not just that, because we use these reference momenta, we got rid of one diagram here. This was a very simple calculation, so it's not that difficult, but we still got rid of half the diagrams, right? So this is really the result of the gauge symmetry that we already talked about. So in this case, we're really using the gauge redundancy, to our advantage. So we're using the gauge symmetry to our advantage. The gauge symmetry let us use this reference spinner. And by a good choice of the reference spinner, we can cancel many diagrams. Okay, another nice thing about this was that the manipulations are very easy. And essentially, you're just working with some complex numbers and squaring the amplitude is very easy. Okay, but this is really the main thing, the fact that choosing these reference spinners let you get rid of many of the diagrams. And this is really also the clue that we already mentioned to the power of these methods and why you want to go on shell. So if you think about QCD, where this is most important, there's a very nice review, a very old review by Mangano and Park, where they have a very famous table. And what they give you in this table is the number of Feynman diagrams that contribute to glue goes to n gluons. This is a tree level. And the numbers really stand for something that's called color ordered amplitudes that we'll talk about very soon. But let me just show you the numbers because they are impressive. So for n equals 2, 3, 4, up to 8, the number of Feynman diagrams that you have are 4, 25, 220, and then 10 million, 525, 900. So this is a lot, okay? And the number grows very fast. But in some cases, you get a very, very simple answer. So there are some cases for which you can write the full compact results for n number of, for n gluons in the final state. The simplest one, when they're all the same helicity, all plus or all minus. In this case, you just get 0, which is a very simple result. When you have 1 minus and all the rest are plus, you again get 0. And when you have 2 minuses and any number of pluses, this is the first time that you get something non-zero, but it has a very, very simple form. You can write it as 1 to the 4th divided by 1, 2, 2, 3, and so forth, and so on and so forth, up to n1. So, you know, if you're summing lots and lots and lots of diagrams, and at the end of the day, you get something that looks like this, that's kind of your clue that there's something not very efficient about the Feynman diagram calculation in this case. And this is really why these methods are so powerful, because you concentrate on the physical degrees of freedom, and that gets rid of all the gauge redundancy. Now, these amplitudes are the first ones that are non-vanishing, when you start switching some gluon helicities from pluses to minuses. So they're called the maximally helicity violating amplitudes, or in short, MHV. So the all pluses violate helicity in the worst way, and then these are the ones that are minimally helicity violating and still non-zero. And we're going to talk about them some more. Okay. Now let's do one more thing that I want to say about this. Again, this is just a complex number, right? So it's a very compact expression for the amplitude. We can also count dimensions. So remember that this any one of these spinor products, its dimension is 1, its mass dimension is 1. So what we have here is the dimension of this expression that we got here is 4 minus n. And 4 minus n is exactly the dimension of the endpoint amplitude. So maybe I didn't say this clearly enough. This is 1 to up to n. This is n external gluons. And this is an important exercise that you should really check. You should really convince yourself that if you're looking at an endpoint amplitude, its mass dimension is 4 minus n. So this amplitude that we got here is consistent with having a coupling that's dimensionless, right? We have some power of the coupling here, the gauge coupling, but the gauge coupling is dimensionless. So this is indeed the right thing for QCD. Of course, if we had another scale in the problem, then we could have other structures that are allowed here. And actually, although this is an n-gluon amplitude, you'll see that, either today or tomorrow, you'll be able to show that this is indeed the correct expression for that. Okay. So what this really suggests is that there has to be a better way of calculating QCD amplitudes or gauge theory amplitudes more generally. If we just concentrate on the physical degrees of freedom. So that's what we're going to do next. So the thing we want to do next is we want to look at the interactions of massless spin 1 particle. Okay, but let me see if there are any questions before that.
Questions here.
Okay, good. So it's all clear.
Yeah, I have a question. Okay. Can you turn back on the previous page? Do you hear me? Yeah. So the n that you're using after, and the n it's the total number of gluon, so it would be n plus 2 on the notation that you're using on the upper half of the page. Am I correct?
So yeah, the total number of gluons here is n. There's 2 minuses and n minus 2 pluses.
Yes, so before it would be glue,
yeah,
n minus 2 glue, right?
Right, so there's something I haven't told you yet about what this amplitude really is. Which is related to what you're asking about, the ordering or the permutations. So it corresponds to a particular ordering of the gluons. So we can, we'll come back to that.
No, my question was much more stupid actually. When you write number of Feynman diagram for glue going to n glue, it's not that n is not the total number of gluon, but in the rest of the page. Okay, just to be clear if I understand. Okay, thank you.
Exactly. Yeah. So this huge number here is really for 10 gluons altogether.
Okay. Okay. Thank you.
Yeah.
I also have a question. I got a bit confused about this epsilon minus polarization. And regarding when you talked about little group rate, so in the epsilon minus, we had this R square bracket in 2 directions, and I thought you made the point that the rephasing of the R should drop out somehow, but I don't see it in this case for the epsilon minus. I think it's 2 or 3 pages before this one.
But Gustavo, can you repeat the question for me, because the sound isn't that great?
I can also try without the mask, then maybe better. So in the epsilon minus case, I don't see how the rephasing would drop out for the reference momentum. So for if we want to have the Lorenz group rate, for example, then in the epsilon plus case, you made the point that if we rephase the R angle bracket and in the numerator and the denominator, then the phase would drop out, but I don't see it in the epsilon minus case.
I'm sorry, the sound is not very good, so I cannot understand the...
I'm gonna try myself. Maybe the Spanish accent helps. I don't know. So I think the question is, in the epsilon minus case, he doesn't seem to understand how the phases drop out. Is that the question? For the reference frame, right? He doesn't seem to understand how the phases drop out in the epsilon minus case. In the epsilon plus case, yes.
So the question is about the negative polarization?
Yes, and so he doesn't seem to understand how the phases drop out in the epsilon minus case.
In the massless case?
If you go forward, one more.
So, you don't understand what's going on?
This R angle, so where this dropped out basically the weight for the little group. And for the epsilon minus case, we have somehow the square bracket in different directions. So I don't see how this drops out in the phase, basically.
Okay, so let me see. So remember this, now we're talking about a photon or a gluon that has momentum k. That's the only physical thing. And this R is completely arbitrary. R is something that's completely not physical. So the end result should not depend on this R. It's really like a choice of gauge. So, you know, that if you, there shouldn't be any real, we can't think of it in terms of its little group weight or anything like that. But if you're counting, if you're naively counting little group weights, then you see that the R appears exactly in the same way upstairs and downstairs. So there cannot be, so it's completely neutral with respect to that.
The question
okay, there should.
the question seems to be that in the epsilon minus, it doesn't appear the same way upstairs and downstairs. That seems to be the question.
Sorry, so the question is about the
other case, the other polarization, the minus polarization. So if you do the minus polarization instead of the plus, is that going to?
Oh, are you worried about just exchanging squares and angles?
Yeah, I suppose that's the question.
Okay. Oh, it could be that I just, you know, that I mixed it up. That's totally possible. The only thing that the only thing that's really important here, so it could be that I mixed up pluses and minuses. The only thing that's important is that for one guy, you know, if you have the K here, then you should have the KR here. And for the other guy, if you have the K here, then you should have K. Sorry, so let me write it like this. So the physical momentum K has to appear one upstairs with a square and downstairs with an angle, or vice versa. And whether I mixed up my pluses or minuses, there's a very good chance that I did that.
Okay, so maybe they should work out the details in their free time.
It's just a matter of conventions, really. I mean, you can just change the helicity weight for plus or minus. Of course, there is a well-defined notion of what's positive helicity and what's negative helicity. But yeah, I mean, it's possible that I mixed them up here.
Okay. I don't see any more hands up. Oh, one more here.
So probably another stupid question about this polarizations. So when we wrote down the epsilon mu ij, there was a sigma mu, and when we changed the notation to go to the alpha alpha dot instead of mu, the Pauli matrix was gone. Like, what happened to it? Where did it disappear to? Probably it's very obvious, but I didn't get it.
Okay, so so I think you're asking, so in general, if I write some, so suppose I have some vector v mu, I can write it as v mu, and I can write it as v alpha alpha dot, which just means that I'm contracting it with a sigma mu alpha alpha dot. So I can go back and forth between something that has, for example, we can have an epsilon mu where we had something with, let's say, an R sigma mu K divided by something, and then I can write it as epsilon alpha alpha dot by taking this guy and contracting with sigma mu. So there's a little bit of algebra involved in that. So I think this is something that you can do as an exercise. You have all the ingredients that you need in order to do that. But essentially, we can really go between these two ways of writing it by multiplying by sigma mu.
Okay, thanks. I was just not aware that going to v alpha alpha dot already contains a contraction with the Pauli matrix. Thanks.
Okay, I think we can continue.
Okay. Okay. So right. So we want to look at the interactions of massless spin 1 particles. And let's imagine that we have some theory in which we have n massless spin 1 particles. Of course, if they're all massless, it means that they're degenerate. And if there's nothing else in my theory, then there's no difference between them. I can tell them apart. So that means that I have some symmetry that essentially exchanges any of these guys. Or in other words, they're just like, they are essentially identical particles. And so if you want to think of something concrete, you can think about gluons in this context, or photons, or W bosons in the unbroken phase. And there's nothing else in the theory besides these guys. Okay, so when we think about their interactions, the first thing that we need are the 3-point amplitudes. So let's construct these. And actually, because it's going to be fairly simple, we're just going to construct all the 3-point amplitudes of meshless particles. It's really not very complicated. So the first thing to note is that we have so we're looking at some 3-point amplitude with 1, 2, and 3. And if you think about this, or you probably know this already, you can't have P1 plus P2 plus P3 equals 0 when all your momenta are light-like. And again, if this is something that you don't immediately recognize, then you should convince yourself that that's really the case. So this is not something we can do with real momenta, but we're going to consider complex momenta, and then there's no problem. Okay, let's think about this in terms of spinors. So in terms of spinors, for example, if I say P3 squared has to be equal 0, I know that P3 squared is equal to P1 plus P2 squared, and this is equal to 1, 2 times 2, 1. So that tells me that either this guy is 0 or this guy is 0. So suppose for a second that it's 1, 2 angle that's non-zero. Now let's look at 1, 2, 1, 3. So I can write this as 2, 1, 3, just like we did for Compton scattering. And now I can use momentum conservation. So I can replace 1 by 2 plus 3. And now I have 2 acting on this spinor, 3 acting on this spinor, and the whole thing vanishes. So we learned that in this case, 1, 3 is 0. So if we assume that 1, 2 angle is 0, we find that we can repeat the same story for 2, 3, and we find that all these guys vanish in this case. So that's a very special property of 3-point amplitudes. The 3-point amplitudes are the simplest ones, but they're the trickiest one in terms of their kinematics. So for the 3 points, we either have ij non-zero or ij non-zero, either the squares or the angles. So either we have what's called all square kinematics or an all, sorry, other way around, of course. Let me change that. All angle kinematics. So I mean this thing, of course. Okay, either just squares or just angles. And what that means is that, for example, if we're in the all angle kinematics, so all my squares here are 0, that means that the 3 spinors 1 and 2 and 3, they're all proportional to each other. And similarly, if we're in all square kinematics, then all the angle spinors are proportional to each other. Okay, so that's the first thing that we need to know about these amplitudes. Okay, but this is really great because now we know that the 3-point amplitudes are either they just involve angle spinors or square spinors, but then we can use the little group charges that we talked about before. And that's going to completely determine them. So let's talk first of all about, so now we're talking about some 3-point amplitude. let me take, let me label the particles and their helicities. So I have 1 with helicity 1, 2 and 3 with helicities H2 and H3. So now, for example, I can imagine that this A is given by C, some constant, times 1, 2 to some power n1, 2, 1, 3 to some power n1, 3, 2, 3 to some power n2, 3. And that's going to be one possibility. I could also imagine that it's that here I assume that it's in all square kinematics. I can also assume that it's in all angle kinematics. So we'll come back to that in a second. But let me first of all talk about scalars. So suppose we just have 3 scalars. So for scalars, there is no little group weight, right? There is no polarization that's involved. So the amplitude should be completely neutral under the little group. But then you see that, you know, 1 here, we have 1, and here we have 1, and they do carry little group weights. So what we need in this case is for n12 plus n13 to be 0, and similarly for 2 and 3. So in this case, what we find is that all these guys, n12 and so on and so forth, are all 0. So our amplitude is just a constant. Now, I assume that I have a theory of 3 massless scalars. If there's no scale in the problem, then this amplitude better be 0. And the reason is that, remember that what is the dimension of A? The dimension of A, in this case, is 4 minus n, which is 3. So it has mass dimension 1. So this constant here has the dimension of the mass. And since by assumption I don't have any mass or any other scale in this problem, so my A just vanishes in this case. So this is just for a scalar case, but now let's do the full story. So now if we have some particles of non-zero spins with some helicities H1, H2, and H3, we can look at the little group charges under each one of these guys. And so in the general case, we find that N12 plus N13 needs to be equal to 2H1, N12 plus N23 equals 2H2, and so on and so forth. So you can solve these 3 equations for the powers, and you find that A3 is equal to C times 1, 2 to the power H1 plus H2 minus H3 times 1, 3 to the power H1 plus H3 minus H2, and similarly for 2, 3. So let me call this equation star. And then we have a similar story if we have all angle kinematics. If we had all angle kinematics, then we have exactly the same thing with A3 equals C prime times 1 to the H1 plus the other way around, H3 minus H1 minus H2, and similarly for the other brackets. And so now we need to decide which form is the correct form. Is it this form or is it this form? Okay, so this is something that we're going to see now. So let's again look at dimensional analysis. So remember that this is a 3-point amplitude. So A3, its dimension is just 1. And so you can see that the C here, this guy here, has dimension 1 minus the sum of the helicities. And similarly, C prime has 1 plus the sum of the helicities. And that's the end of the story. Because now we can check whether these guys have 0 or positive or negative mass dimensions. So what we want to have is C or C prime. They have to have 0 or negative mass dimension. And the reason is that we expect our couplings to correspond to renormalizable or non-renormalizable interactions, but we don't expect them to be associated with super renormalizable interactions. If we find that we have a coupling which has a positive mass dimension, then it's coming from some non-local interaction that would involve some term in the Lagrangian that goes like 1 over some derivative. So that's not something consistent. So that's going to tell us which one of the forms this is. So if the sum of helicities is greater or equal to 1, then we live in the square kinematics. And if it's the other way around, if it's smaller than -1, then we have angle kinematics. So that tells us which one of these possibilities is realized. But you see what happened. What happened is that up to some coefficient, we now have the full list of 3-point amplitudes for any particle spins. There's another way to say the same thing, which is that suppose I take all my momenta, I have the 3 momenta P1, P2, and P3, and I rescale them together. If they all go to 0 together, I expect the amplitude to go to 0 and not blow up. So that's going to do, that's going to reproduce exactly the same thing that we now got in terms of determining whether it's square kinematics or angle kinematics. But other than that, we're done. We now have all the 3-point amplitudes for any massless particles. Okay, so questions about this?
Any questions about this? I don't see any hands, so I don't know.
So I think, because I lost some time over my technical problems, can we have 5 more minutes? So I'll go on a little bit. I still have like a few more minutes.
Sure.
Okay.
Sure.
Good. Okay, so now that we did all this work, we should really start to see more results. And remember, the thing that we were interested in are the interactions of spin 1 particles. So now let's imagine that we have 3 spin 1 particles. And this is their 3-point amplitude. So this guy is going to be 1, this guy is going to be 2, this guy is going to be 3. And I'll label them by their momenta, helicities. And remember, I had a bunch of them. Suppose I in such particles. So let's also give them some index A, where A runs from 1 to N. So this is going to be A, this is going to be B, and this is going to be C. And they also have their helicities H2 and H3. And so now we can start to look at their amplitudes. So let me first of all take them all to have the same helicity. Let's say plus. Okay, so we calculated the amplitude. We know by now that it's proportional to 1, 2, 2, 3, 3, 1. It's coming with some coefficient C. And there's something that needs to carry their ABC indices. So I'm just going to call it CABC. Now, what is the dimension of this guy? The dimension of this guy, remember, this is, each one of them has dimension 1. The amplitude is dimension 1. So this has to go like 1 over lambda squared, where lambda is some mass scale. So you see that this is something that's appropriate, that looks like a dimension 6 operator. So I can, so this is coming from some, if I'm thinking about operator contributions in the Lagrangian, this looks like a dimension 6 operator. And so let me put a 6 on this CABC. But now there's another thing that we notice, which is that we have n identical bosons. And so the amplitude has to be symmetric under the exchange of any one of them. But on the other hand, if I exchange 1 and 2, for example, I get a minus sign from here. But these two guys just get exchanged. So this kinematic factor is anti-symmetric under the exchange of any I and J. So that means that if I exchange any two of the gluons, the CABC here needs to be anti-symmetric too. So this CABC has to be anti-symmetric under exchange of 1, 2, or 3, any pair of them. So there are two immediate things that we learn from here. The first thing is that there's no such coupling for photons, because I just have, for a photon, I just have a single guy. There is no n equals 1, and so there's nothing anti-symmetric that we can construct. Another thing that we see is that we need at least 3 of these guys. We need at least 3 particles in this multiplet. So that's very interesting, but now let's look at a different choice of felicities, which is even more interesting. And let's look at the amplitude where, for example, we take 1 to be plus and 2 and 3 to be minus. And in this case, we can, again, go through the same thing, just substitute in the same amplitude. Now we have some C, 2, 3 squared divided by 1, 2, 1, 3, and times another C ABC. And first of all, you can convince yourself that the dimension of this guy is just 0. So it's consistent with being a renormalizable coupling. And the other thing that you can notice is that, again, if you exchange 2 and 3, this thing is anti-symmetric. So the CABC has to be anti-symmetric under the exchange of B and C. But now also I can repeat the story by using crossing symmetry and conclude that the CABC, again, is anti-symmetric with respect to exchanging 1, 2, 2, 3, and any other pair. So it's a totally anti-symmetric tensor. So what have we learned? We learned that the renormalizable interactions of such spin 1 massless particles is totally anti-symmetric. Or let me say this a little more carefully. This interaction is proportional to some structure that is totally anti-symmetric in the indices A, B, and C. So what we're starting to see is exactly the structure constant that we're used to of SUN, or more generally any Lie group. We also see that we need at least, again, 3 particles in this representation, in this multiplet, in order to have some non-trivial representations. And so you see exactly that the smallest structure that you can have here is something with 3 massless spin 1 particles corresponding to an SU2. That's the lowest, the smallest group that you can have here. And you see that what we're really starting to see here are Lie groups, because these interactions involve these structure constants that are completely anti-symmetric. So what do Lie groups involve? They involve, first of all, the structure constants that are totally anti-symmetric. And then the structure constants also need to satisfy the Jacobi identities. And these 2 things together allow you to classify all the simple Lie groups. So this part we already see. This part we're going to see next time. And you see that this is a very powerful result. And actually, I think this is one of my favorite cases for seeing the connection between mathematics and physics. And I remember from, the days that I was a student and I was reading some math book about group theory. I can't remember which one it was. And there was this really nice quote there about how Lie and his friends were super happy when they discovered Lie groups, because they said, okay, finally, we have something that the physicists are never going to be able to lay their hands on. So if you think about the place that Lie groups have in physics, it's a very, very central place, obviously. But here it's really nice to see how you recover them by looking at something very, very physical. Just looking at the interactions of physical spin 1 massless particles, and this structure just emerges from that. So that's really satisfying. So I think we'll have to stop here, and next time we'll see the rest of the story, namely the Jacobi identity. The way the Jacobi identity is going to come up is when we look at 4-point amplitudes. Okay, so I think I'll stop here.
Thank you, Yael. Thank you very much for this wonderful lecture. Any more questions, comments, complaints? I didn't know this quote is wonderful. It makes me want to say something like Lie may be saying, we would have gotten away if it wasn't for those meddling physicists. Sort of a Scooby-Doo quote for the... Any more questions, comments? No? Okay, so let's go then for our break until 11:15. We could return for Chava Chaki's next lecture. Thank you, Yael.
Thank you. Bye-bye.
And let me, okay, sure, go ahead.